This video we're gonna go through the solution for homework 11. So let's look at the first problem 10.8. The hair loss from section 1 to 2 is 1 meters. So the friction loss is 1 meter. The Darcy friction factor is 0.01, so F equals to 0.01. D is 1 meter. The length L is 100 meter. So it says the flow is steady and fully developed. Calculate the mean velocity in meter per second. Choose the closest answer. So to find the velocity, we're gonna use the Darcy-Weisberg equation. HF equals to F times L over D times V squared over 2G. So the velocity will become square root of the hair loss times D times 2G over F times L. So the hair loss is 1 meter, diameter is 1 meter times 2G over the friction factor, which is 0.01 times the length, which is 100 meter. Okay, so the velocity is gonna be 4.42 meter per second. So we're gonna choose D. Now let's look at second problem 10.10. Water at 15 degrees Celsius flows through a garden hose with a mean velocity of 1.5 meter per second. Find the pressure drop for a section of hose that is 20 meters long and suited hose horizontally. Assume that the friction factor equals to 0.012. So for this problem, we have the temperature at 15 degrees Celsius. So the density of the water gonna be 999 kilogram per cubic meter. And diameter is provided, which is 25 millimeter, which is 0.025 meters. And the velocity is 1.5 meter per second. And the length of the pipe is 20 meters. And friction factor is 0.012. So with those information, first thing we're gonna do is find the friction the friction loss between the two ends of the pipe. So we're gonna use the Darcy-Weisberg equation. HF equals to F times L over D times V squared over 2G. So the friction factor is 0.012. The length of the pipe 20 meters. The diameter of the pipe 0.025 meters. And times the velocity 1.5 meter per second. Power of 2 over 2 times G. So the friction factor the friction loss is gonna be 1.1 meter. Okay, So now we have the friction loss. The problem is asking us to find the pressure drop. So we're gonna use the energy equation between the two sections of the pipe. So P1 is the starting point plus V1 square over 2G plus Z1 gonna equals to the end point, P2 over gamma plus V2 squared over 2G plus Z2 plus the head losses. And because it's the entire thing is suited horizontally, so the Z should be the same. So we can cancel it out. The velocity, because the velocity should be constant, so the velocity heads should also cancel each other out, and we will only have the pressure term and friction factor, friction losses. So P1 over gamma minus P2 over gamma equals to the head loss. Okay. So P1 minus P2 equals to the head loss times the gamma, which is also delta P. Gamma is rho times G. So the head losses is 1.1 meter times 999. 2 times G so the pressure difference is gonna be 10.8 kilopascal. Now let's look at problem 3, 10.24. So we have a pipe system here. We have two different pipes. The diameter of the pipe is different. One is 1 meter, the other is 2 meters. So the problem is asking what's the ratio of the head losses. So we're gonna use the Darcy-Weisberg equation for both of the pipes. So let's say the friction loss of pipe 1 is gonna equals to F1 times L1 over D1 times V1 squared over 2G. Okay, and head loss for pipe 2 is gonna be F2 times L2 over D2 times V2 squared over 2G. Okay, so now we're gonna put them together. HL1 over HL2. So this is the ratio of the two pipes. So from the figure, we can know the friction factor for both pipes is the same, which is 0.01. So in the ratio, they will cancel out. And the length of the pipe is also the same. So the L terms will also cancel out. Of course, the G gravity is also the same. So the ratio will be simplified to D2 over d1 times v1 squared over v2 squared. Okay. So from the continuity equation, we can know a1 times v1 should equals to a2 times v2. So a1 is pi over 4 times d1 squared times v1, which equals to pi over 4 d2 squared times v2. Okay. So we know the diameter ratio is 1 for pipe 1 and 2 for pipe 2. So the velocity ratio gonna be v1 over v2 gonna be d2 squared over d1 squared. Okay. Now we're gonna back substitute it to the friction ratio. HL1 over HL2 gonna be d2 times d1 times d2 squared over d1 squared. And it's the power of 2. Okay. So the entire thing can be simplified to d2 d1 to the power of 5. So when the ratio is 2, the head losses ratio will actually be 32. So we're gonna choose D. So now let's look at problem 10.14. So in a 4.2 inch uncoated cast iron pipe, 0.08 cubic feet per second of water flows at 60 degrees Fahrenheit. We're going to determine the friction factor using the figure 10.14. So the diameter is 4.2 inch. Okay, so and the Q is 0.08 cubic feet per second. So from table 8.5, we can find the viscosity equals to 1.22 times 10 to the negative 5 feet per second. And from table 10.4, we can find the Ks value equals to 0.01 inch for cast iron. So this is the roughness. So the first thing we're gonna do is find the Reynolds number. Re equals to 4 times Q over pi d times the viscosity. So 4 times the Q is given 0.08. And times the pi pi here times the d. So we're gonna convert the d to feet, from inch to feet. Feet and times the viscosity, 1.22 times 10 to the negative 5 feet per second. So this gonna gives us the Reynolds number, which is 2.39 times 10 to the power of 4. Okay, and to use the figure 10.14, we can also have the relative roughness Ks over D, which is gonna be 0.01 inch over 4.2 inch. So this is gonna be 0.00238. Okay, now we have all the information to use 10.14 figure. So we're gonna look at here. So for the Ks number, we have 2.38, so it'll be probably somewhere here. We're gonna follow this line here. Okay, and for the Reynolds number, is somewhere at 2.39 times 10 to the power of 4. So here is 2 times 10 to the power of 4. So 2.39 will be somewhere here. If we follow the straight line, and it will give us a number that's relative equals to 0.03. Now let's look at problem 10.47. So we have water flows with a speed of 5 feet per second. So we have V equals to 5 feet per second through a horizontal, is through a horizontal pipe. The length of the pipe, L, equals to 100 feet. The pipe diameter with the nominal diameter of 2.5 inch, so the actual diameter should be 2.45 inches, which is equals to 2.45 divided by 12 feet, which is 0.24 feet. And we're gonna calculate the pressure, drops and head loss, and power need to overcome the head loss. So to start with, we're gonna find the Reynolds number for this problem. So we're gonna need to know the viscosity, which it's 50 degree of Fahrenheit, should be 14.1 times 10 to the negative 6 feet per second. Okay, so the Reynolds number should equals to V times D over the viscosity. The velocity is 5 feet per second. The diameter is 0.24 feet. It's over the viscosity, 14.1 times 10 to the negative 6 feet per second. So our Reynolds number is 72,400. So which means the flow is turbulent. So for turbulent flow, we have a friction factor that's equals to 0.25 over 10 times 5.74 over the Reynolds number to the power of 0.9. Okay. The entire thing to the power of 2. Okay, so now we can plug numbers in. Log 10 times of 5.74. The Reynolds number is 72,400 power of 0.9. So we will have a friction factor of 0.0191. Okay. Please note that this equation is only valid for turbulent flow. So for if it's not turbulent, we will have other term in the log function. So we need to find the Ks and D values to do the calculation. So now we have the friction factor. We can find the head loss of the friction. So it's gonna equals to F times L dE times V squared over 2G. Okay, so F is 0.0191 times the L, which is 100 feet. The diameter is 0.204 feet. The velocity is 5 feet per second. G is 32.2. So the head losses is gonna equals to 3.635 feet. Okay. So we have actually find the part B first. Now we're gonna use the energy equation to find the answer for part A. So P1 over gamma plus V1 squared over 2G plus C1 gonna equals to P2 over gamma plus V2 squared over 2G plus C2 plus the head losses. Okay. It should be HF for this problem. And because the velocity should be the same, because it's the same pipe, and it's horizontal pipe, so the elevation should be the same. So the only thing we have, the delta P, is gonna equals to gamma times the head losses. Okay, which is our gamma is 62.4 pf per cubic feet times the head loss 3.635 feet. So the pressure difference is gonna equals to 0.27 psf. And if we convert that to psi, we're gonna equals to 1.58 psi. Okay. And now we're gonna find the power that can overcome the hair loss. So P equals to Q times gamma times the head over 555. Notice this constant is only for English unit. So for SI units, you actually don't have the 550 term. Okay, so we have the velocity, but we still don't have the Q. So Q equals to A times V. A equals to pi over 4 times diameter, which is 0.24 feet squared times the velocity, which is 5 feet per second. Okay. That's gonna equals to equals to 0.1634 cubic feet per second. And back substitute it to the power equation. Q is 0.1634 cubic feet per second times gamma, which is 62.4 BF cubic feet times the hair losses 3.635 feet over the 550. So it will convert it to the horsepower, which equals 0.0675 horsepower. Now let's look at the last problem, 10.153. The water is pumping from a reservoir to a pressurized tank. So the steel pipe is 4 diameter, so D equals to 4 inch, which is 1/3 feet. And the length of the pipe is 300 feet. Okay, so the discharge is 1 cubic feet per second. So it says the pressure at tank B, so PB here is equals to 10 psig. And the tank A is open to the atmosphere, so PA should be equal to 0. And the pump efficiency is 90%. So those are the basic informations. And we have the pipe material is steel, so from table 10.4 we can find Ks equals to 0.002 inch. Okay, so Ks over D equals to 0.002 inch divided by D, which is 4 inch, which gives us 0.0005. Okay, so the viscosity gonna equals to 1.22 times 10 to the negative 5 squared per second. And from table 10.5, we can find the friction factor K lowercase e, which is the head loss coefficient from the tank to pipe, is 0.03. And K uppercase E, which is the head loss factor from pipe to the tank, equals to 1. Okay. So for all the information here, I'm gonna find the velocity and Reynolds number in order to use our Moody's diagram to define the friction factor. So the velocity equals to Q divided by A, which is 1 cubic feet per second divided by pi over 4 times squared which is gonna be 11.46 feet per second. And the Reynolds number equals to VD over rho, over the viscosity, 1.46 feet per second times diameter, which is 1/3. The viscosity is 1.22 times 10 to the negative 5 feet squared per second. So the Reynolds number equals to 3.13 times 10 to the power of 5. Now we have the relative roughness, which is this one, and the Reynolds number. We can use them to find our friction factor F. So if we look at the figure here, the Reynolds number 3.31 should be somewhere here. So we draw a straight line, and relative roughness is 0.005, so it's between the 0.04 and 0.06. So we go like this. So we can find it somewhere here. So for this value, it's 20. It's between the 18 and 19. So we're gonna say the friction factor F is equals to 0.0185. Okay. So now we can write down the energy equation. P1 over gamma plus V1 squared over 2G plus C1 plus the pump head equals to P2 over gamma plus V2 squared over 2G plus C2 plus the head losses, so the entrance, the exit, and the friction losses. Okay. So if we move the equation, so if we do the simplification first, V1 and V2 at the water surface 0. C1 and C2 should also be 0. and it will gives us only the pressure and the friction loss and the pump term. So HV should equals to the delta P over gamma plus K entrance plus K exit plus friction factor over 2G. Okay. So the pressure difference is 10 psig. If we convert that to feet unit, it will be 40 inch squared feet squared over the 20.4 feet, which is the gamma, plus the K entrance 0.03, K exit 1, and friction factor 0.0185. The length is 300 feet, and diameter is 1/3 feet times the velocity, which is 0.46 to the power of 2 over 2 times the G. Okay. So the pump head should equals to 59.13 feet. Okay. And we're gonna convert that to power unit. So P equals to Q gamma times the pump head over 550 for English unit. And we have the efficiency as well, so divided by the efficiency. The Q is 1 cubic feet per second. The gamma is 62.4. And the pump head is 59.13 feet over the 55 times 0.9, which gives us 7.45 horsepower.